Assalamualaikum girls. I am Shamsunisa from Royal Degree College, Chemistry Department. Today in Unit 2, Organic Chemistry, Chapter 1, Amines, Cyanides and Isocyanides, we will go through physical properties of amines, basic nature of amines, comparative basic strength of ammonia, methylamine, dimethylamine, trimethylamine and aniline. Then amine salts as phase transfer catalysts. Now we'll see the physical properties of amines. So lower members are colorless gases at room temperature. And the higher members of amines, that is C4, the carbon 4 onwards, they are volatile liquids, and still higher members are colorless solids. Aromatic amines are colorless liquid and solid and turn brown in air. Means when they are in contact with air, they will show the brown color. Aliphatic amines with lower molecular weight or lower molecular mass have strong smell of ammonia. They are lighter than water. Primary amine and secondary amine exhibit intermolecular hydrogen bonding. Tertiary amine do not form hydrogen bonding. Due to these, primary and secondary amines have comparatively high boiling point as compared to tertiary amine. Here you can see primary amine structure. This one is R, single bond N, single bond H, single bond H. Another primary amine, second molecule of the primary amine. In between the two primary amine, in between nitrogen of one primary amine and hydrogen of another primary amine, discrete bond is going to form. That is nothing but intermolecular hydrogen bonding, you can see. This will be there in case of primary amine and as well as in case of the secondary amine. But in case of the tertiary amine, this intermolecular hydrogen bonding will not be present. Aliphatic amines are soluble in water. They form hydrogen bonds with water molecules. Aromatic amines are almost insoluble in water. They do not form hydrogen bond with water. Next is basic nature of amines. Amines are basic in nature, like ammonia, due to the presence of a lone pair of electrons on nitrogen. Amines, being stronger bases than water, can be easily protonated by water in their aqueous solutions. Like ammonia, amines also give OH- ions in aqueous solution. Here you can see the reaction. As we are taking here RNH2, this is the primary amine in which we are adding water molecule. On reversible equation, what will happen here? One hydrogen from water molecule is being added to the primary amine. So we are getting here RNH3 plus. Along with that, OH- ion we are getting from the water. The strength of a base can be known from the value of its dissociation constant. Dissociation constant for the base, it is represented as Kb. For the above reaction, like this we can write the equation. Kb, it is equal to molar concentration of RNH3 plus and the concentration of OH minus divided by RNH2. By seeing that particular equation, the previous equation, molar concentration of the products, it should be divided by molar concentration of the reactant. Here we are not considering the water molecule in the reactant. Why? Because it is negligible. This one is negligible. Then greater the value of Kb, greater is the strength of the base. The strength of a base can also be expressed in terms of pKb value. pKb, it is equal to minus log Kb. Thus, smaller the pKb value of a base, greater will be its basic strength. If the pKb value is greater at that time, the smaller will be its basic strength, or lesser we can say its basic strength. Next is comparative basic strengths of ammonia, methylamine, dimethylamine, trimethylamine and aniline. The basic nature of amines and ammonia is due to the availability of lone pair of electrons on their nitrogen atom. Easier the availability of lone pair of electrons, greater is the strength of base. So aliphatic amines are stronger bases than ammonia. Why? Because the alkyl group in amine is electron releasing group. That is, it has plus I effect. Plus I means positive inductive effect it will show, which causes greater electron density on its nitrogen atoms. Aliphatic amines can donate their lone pair of electrons more easily than ammonia. Hence, aliphatic amines, that is nothing but alkyl amines, are more basic than ammonia. Due to the combined effect of plus I effect of alkyl group, hydrogen bonding and steric factors will determine the stability of the ammonium cation in solution. These factors favor secondary amine and make it the strongest base. So because of that reason only we can say that secondary amine it is considered to be as the strongest base as compared to that of the primary amine. The overall decreasing basic strength of methylamine is secondary amine, that is CH3 taken twice NH, dimethylamine, which is nothing but secondary amine. It is more basic compared to that of methylamine, which is nothing but a primary amine. And this methylamine, it is more basic compared to that of trimethylamine, which is nothing but a tertiary amine. Next is in non-aqueous solvent, we will see. The solvation effect or the stabilization of conjugate acid is due to the absence of hydrogen bonding. Here the basicity of amines will depend only on the plus I effect of the alkyl group. Basicity of amines in non-aqueous solvent follows the order. Like this it will follow the order. Trimethylamine, that is second, the tertiary amine, which is more basic compared to that of dimethylamine, that is nothing but secondary amine. This secondary amine is more basic compared to that of primary amine, that is methylamine, and this methylamine it is more basic compared to that of ammonia. In the case of aniline, the benzene ring exerts an electron withdrawing influence on amino group due to resonance. This decreases the availability of the lone pair of electrons on nitrogen for protonation. Thus, basic strength decreases. Aryl amine with alkyl substituents at nitrogen atom are slightly more basic than simple primary aryl amine. N-methyl and N-dimethyl are slightly more basic than aniline. Means here if we will compare the N-methyl and N-dimethyl with aniline, both which one? N-methyl and N-dimethyl both are slightly more basic compared to that of aniline. The decreasing order of the basic strength in non-aqueous medium is ammonia is more basic compared to that of N,N-dimethyl aniline. And N,N-dimethyl aniline is more basic in nature compared to that of N-methyl aniline. Next is in aqueous medium. Up to this we have seen about the non-aqueous medium, isn't it? Now we are talking about the aqueous. In aqueous medium, N,N-dimethyl aniline will be less basic because nitrogen atom does not carry any hydrogen and there will be no hydrogen bonding with water molecule. Next we'll see about amine salts as phase transfer catalyst. In phase transfer catalysis, a catalyst is used to carry the nucleophile from the aqueous into the organic phase. Here we'll see the example. Simply heating or stirring a two-phase mixture of 1-chlorooctane for several days with aqueous sodium cyanide gives essentially no yield of 1-cyanooctane. But if a small amount of an quaternary ammonium salt, that is an amine salt, is added in that, what will happen? The product is quantitatively formed in 2 hours. So the use of quaternary ammonium salt brings the anion into the organic phase and allow it to be relatively free to react with the substrate. The uncatalyzed reaction is the reaction which is not taking place in the presence of catalyst between 1-chlorooctane and sodium cyanide does not take place. Why? Because the cyanide ions cannot cross the interface between the two phases except in very low concentration. So the reason is the Na plus ion are solvated by the water and this solvation energy would not be present in the organic phase. In organic phase, water molecule will not be present. So the cyanide ion cannot cross without the Na plus ion. Why? Because that would destroy the electrical neutrality of each phase. To Na plus ions, quaternary ammonium ion, that is R4N plus, with sufficient large alkyl group are poorly solvated in water and prefer organic solvents. If a small amount of such a salt is added, 3 equilibria are set up. Here you can see upper one is organic phase, here lower one is aqueous phase. The reaction will take place in the aqueous media. Aqueous is nothing but water. And in between both organic phase and aqueous phase, interface will be there. See here in the organic phase, Q plus Cn minus, quaternary cyanide ion or quaternary cyanide we are taking here. In that we are adding alkyl chloride. So what will happen? We'll get RCN, that is alkyl cyanide, along with that Q plus Cl minus, that is quaternary chloride we are getting. Okay. So this particular reaction, it will take place in the organic phase. Okay. Then from organic phase to the aqueous phase, Q plus Cn minus, it is being transferred. Okay. It can go from organic phase to the aqueous phase. It will react with sodium chloride, Na plus Cl minus. Okay. It is a salt. It will react with the salt. And as a result of that, we are getting here Na plus Cn minus. Na plus and Cn minus, that is sodium cyanide. And along with that, we are getting Q plus Cl minus. So the Q plus Cl minus from organic phase, it can be transferred to the aqueous phase. Okay. And Q plus Cn minus, it also being transferred to the aqueous phase from organic phase. This is our first step of equilibrium. This one is the second step of equilibrium. And the third step of reaction, it will take place in the aqueous phase. And the fourth step, it is taking place in the organic phase. So you can see here, in case of the first equilibrium state and second equilibrium state, Q plus Cn minus from organic phase, it can be transferred to the aqueous phase through interface. Okay. And Q plus Cl minus, as we are getting a product in the organic phase, it can also be transferred to the aqueous phase as it is. That is Q plus Cl minus. But rest of the things, that is RCl, it can't be transferred from organic phase to the aqueous phase. And in case of the aqueous phase, Na plus Cl minus, it also can't be transferred to the organic phase. As it is the same in the product, you can see RCN, it can't be transferred to the aqueous phase from organic phase. And in aqueous phase, Na plus Cl minus, Na plus Cn minus, it also can't be transferred to the organic phase. So the Na plus ions remain in the aqueous phase and they cannot cross. Okay. But the Q plus ions do cross the interface and carry an anion with them. Like this, at the beginning of the reaction, the chief anions present is Cn minus and Cl minus. You can see here, Cn minus and Cl minus. The chief anions which are present in the starting reaction. Okay. Then the Cl minus ions then get carried into the aqueous phase, that you can see in the equilibrium second. Cl minus, it can be transferred to the aqueous phase. Next is equilibrium 3, if we'll see, that takes place entirely in the aqueous phase. See here, equilibrium 3, it is taking place only in the aqueous phase. Then and allow Q plus Cn minus to be regenerated. All the equilibria are normally reached much faster than the actual reaction force. So, it is the rate determining step. Which will be the rate determining step, girls? The reaction which will take place slow, that particular reaction is termed as rate determining step, or it is known as the reaction of rate determining step. Then in certain cases, the Q plus ions have such a low solubility in water that virtually all remain in the organic phase. In such cases, the exchange of ions takes across the interface. Thank you for listening my lecture.